Hello everyone, welcome to the second lecture on the series for dielectrics. So in the previous class we talked about the formation of dielectric polarization, how dielectric polarization occurs in a dielectric material, and then we introduced a three-field vector relation between the displacement vector which correspond to the free charges, electric field vector which correspond to both free charges and bound charges, and polarization vector which correspond only to bound charges. Now today we are going to discuss about the different types of polarization. So there are basically four different types of dielectric polarization. We are going to start with the first one, that is electronic polarization. Now, in order to understand this one, what you need to do is you have to consider an atom which has nucleus at the center and is surrounded by electrons in different orbits. So this is a basic atomic structure which we all have learned, and we know that in the different orbits there are many number of electrons revolving around this nucleus. Now I am going to consider that all the electrons which exist in the different orbits are like a bunch. This is a huge quantity in a particular material. So whichever is the amount of electron, that amount I am going to consider as a bunch, or now I am going to call it as an electron cloud. So if I consider that electron cloud, I will get a spherical shape. I'll get a spherical shape. So there is a nucleus at the center and all the electrons in the different orbits I am going to consider as an electron cloud, and they exist in a spherical shape. Now, can anyone of you guess why it is in a spherical shape? Why it doesn't take any other shape? This is when there is no electric field applied. So the reason is because the atoms are of spherical shape. So that's the reason that even the electron cloud also takes the spherical shape. Now when I apply an electric field, what's going to happen? Let's see that. So come down to the next figure. So we see that the nucleus remains at the same position and the electron cloud gets distorted, the shape gets distorted. So it was spherical earlier. Now when the field is applied, the electron cloud gets elongated. It becomes like an oval shape. It gets elongated. So there is a distribution of charges now. There is an arrangement of charges now between the positively charged nucleus and the negatively charged electron cloud. So this movement of the charges, you would term it as electronic polarization. Now, going further, let's think about this. How far can this expansion go? That means, can this ellipse-like structure keep on extending till infinity? Or is there any limit? So the limit comes by understanding the structure of an atom. So all these are happening within an atom. So that means this elongation also has to stop at the end of the structure of the atom. Or basically the maximum elongation can go to one side corresponds to the maximum radius of the atom. So it is extendable only till the radius of the atom. But at the same time, when it is extending, we need to remember that there is always a force of attraction happening between the positively charged nucleus and the negatively charged electron cloud. And that's the Coulomb force of attraction. So this kind of polarization, this arrangement or formation of elongated electron cloud, movement of the electron cloud from the positively charged nucleus, is being opposed by the Coulomb force of attraction. Now let's look into a few important points about this electronic polarization. First one, it occurs in all the directions. That means in all different directions or the three dimensions. Next, it occurs within a shorter time. That means it is much quicker. Another one, it's independent of temperature, very important point here. And the opposition is due to the Coulomb force of attraction. Opposition to the polarization happening is due to the Coulomb force of attraction. Now, in the previous class, we did define what is known as polarizability. So, we understood that a dipole moment mu can be represented as polarizability into the electric field. So, n number of dipoles multiplied by their dipole moment result into the polarization. So, in case of electronic polarization, I am going to write it as PE. E is representing the electronic polarization. PE is equal to N number of dipoles multiplied by alpha E, which is the electronic polarizability, and E is the electric field. So PE is equal to N alpha E into E is a representation for electronic polarization. Let's move on to the next one, that's ionic polarization. So in the previous case, when it was electronic polarization, we talked about the different electrons existing in an atom. So this is ionic polarization, so it's obviously going to be related to ions. So let's consider say a crystal which has both positive and negative ions. So you have, when there is no electric field applied, there is an equal space between the different ions. All the positive and negative ions are equally separated, or basically there is a social distancing. So when there is no field applied, all of them are equally spaced. But when I apply a field, they start coming close to each other. So this movement of the ions towards each other results into the ionic polarization. And this movement is being opposed by the ionic bonding force. Like in the previous case, we had the Coulomb force of attraction opposing the electronic polarization. Here in ionic polarization, it's the ionic bonding force which is going to oppose the ionic polarization. Now, exactly in the same way how we define the ionic electronic polarization PE, I am going to define the ionic polarization PI as number of dipoles formed multiplied by ionic polarizability alpha I into the electric field E. So PI is equal to N alpha I into E. Now comes the next one, orientation polarization. So orientation, usually we know that it is related to something related to alignment. So let's see what alignment it's basically. So here this orientation polarization is applicable in the case of polar molecules. So polar molecules, yesterday we already talked about in the previous lecture. It always have a permanent dipole moment. So the charges, the centers of the positive and negative charges do not coincide. So there is always a permanent dipole moment. And when there is no electric field applied, the polar molecules are staying randomly. All of them are arranged randomly. So this is one polar molecule, this is another polar molecule, this is another polar molecule. But when I apply an electric field, all of them rotate and come aligned. All of them come aligned. They rotate by some particular amount and they align in a particular direction. So now, in the previous case, let's consider both the cases, that's ionic and electronic polarization. We did have some force of attraction, that's the ionic bonding force or the Coulomb force of attraction opposing the polarization. So here it's what we saw that is a rotation of the dipoles, the polar molecules, which is going to result into polarization, the orientation polarization. So here the rotation which is happening is going to be opposed by the temperature. So we call this as thermal agitation, opposition to the movement of the polar molecules due to increase in temperature. So if temperature is increased, they are not able to rotate much. The rotation happens only by a small amount. They are not able to come and align. All of them cannot align in the same direction. Now let's see one more interesting aspect here. So we did understand that orientation polarization depends strongly on temperature. It's very strongly dependent on temperature, whereas electronic and ionic polarization were not dependent. And one more point to be noticed is the orientation polarization occurs in gases, liquids and viscous substances. So what's so special about solids? Why can't it occur in solids? So the reason is, in case of solids, we already know that they all are based on the crystal lattice structure. So the molecules are always fixed in their position, and if they have to move, the movement will be always constrained by some forces between the different lattice within the crystal or within the solid. So the lattice forces restrict any kind of rotation. So orientation polarization is basically rotation of the molecules. So rotation cannot happen in the case of solids. So that's why there is no orientation polarization in the case of solids, but occurs in gases, liquids and viscous substances. So for an example, so resultant is, say, let's see that if I consider water, the dielectric constant will be very high, while that of solid ice will be very less, because orientation polarization does not take place in case of solid. So exactly the same way how we represented electronic polarization and ionic polarization, we can also represent orientation polarization. So orientation polarization is given by PO is equal to N, once again the number of dipoles or the number of molecules, into alpha O, which will be the orientation polarizability, into the applied electric field E. Now, since orientation polarization is highly dependent on temperature, this alpha O has a particular relation with the dipole moment and the temperature. So that's given by alpha O is equal to mu square, that's the square of the dipole moment, divided by 3 kT, where K is the Boltzmann constant. We already know 1.38 into 10 power minus 23 joule per Kelvin, and T is the temperature acting upon. So alpha O is equal to mu square by 3 kT, or orientation polarization is inversely proportional to temperature. So that means any increase in temperature can result in decrease of orientation polarization. So now we come to the last type of polarization, that is space charge polarization. So space charge basically is, space is referring to position, movement with respect to position, movement in space of the charges. So polarization occurring to movement of charges in space or their position. So this takes place in case of heterogeneous materials, or wherever, if suppose it is an homogeneous material and it has any kind of impurities. In a simple sense, I can say that wherever there is a mixture of materials. So whenever there is no field applied, let's consider here, so there is an electrode at both the ends here of this is one material, and inside is another kind of material which has some charges, positive and negative charges. So this is when there is no electric field applied, and when an electric field is applied, you can see that the charges get aligned, or they move towards this junction between the first material and the second material. So junction, or I can also say as the interface. So this kind of polarization is known as space charge polarization, movement of the charges in space, that means with respect to position. Or another term is interfacial polarization or migrational polarization. Migration in the sense from one material to another material, the attempt to move from one material to another material. So in total, it should be the total polarization should be the sum of all the different types of polarization which we have considered. But this space charge polarization has very negligible contribution. Hence, the total polarization I can represent as electronic polarization Pe plus ionic polarization plus orientation polarization. So that means P total is Pe plus Pi plus Po. Now, with this understanding, let's see what will be the how will be the temperature dependency of polarization. How can I make a curve of it? How can I make a plot of it? So basically we know that electronic and ionic polarization are very much independent of temperature. So the only temperature dependency comes from the orientation polarization, which is PO is equal to N alpha O into E, and alpha O was mu square by 3 kT. So I am going to draw total polarization with respect to 1 over T. And this will be a linear dependency. So you can just see that it's N alpha O into E. If I write instead of alpha O, if I write its value, that's mu square by 3 kT, I get N mu square by 3 kT into E. N will be constant, mu square again a constant, 3k again a constant. So it's directly proportional to 1 by T. So the total polarization will be proportional to 1 over T. So if I plot, I will get a linear relation, and the slope of this curve will give me the value of N mu square by 3k. And the intercept will result in N alpha E plus N alpha A, or N into alpha E plus alpha I. So the total polarization is having a linear dependency with respect to 1 over temperature, and it's a positive linear curve which we are going to get. It's going to be a positive slope. So exactly similar to how there is a temperature dependency, there is also a frequency dependency. So we said that electronic polarization occurs very fast. It occurs in a shorter time, whereas ionic polarization takes a bit more time and orientation takes much longer time. And you always know that time is inversely proportional to frequency. So before we come into the frequency dependency curve, we need to learn something called as a dielectric loss. So what is this dielectric loss? So any kind of energy loss, any kind of energy being dissipated or absorbed, you call as energy loss. So basically we have heard of something called as power loss. So whenever there is an dissipation of power, we call it as power loss. This is in the case of a conducting material. Now in the case of dielectrics, what we are going to see is that there will be more loss when there is an AC field applied, but due to DC it will be very less. So whenever there is an AC field or an AC voltage applied, there will be more amount of absorption of electrical energy by the dielectric material. So this you call as the dielectric loss. And any form of dissipation of energy will turn into heat. So what we are going to do is, I am going to consider a capacitor which is having a dielectric in between and apply an AC signal across it. So since it is an AC signal, so that means it has a particular amplitude and a frequency. So if angular frequency is omega and the applied sinusoidal voltage or the amplitude is V, then the total current flowing through this capacitor I can write into two terms. One is J omega CV, where J is actually representing the imaginary part. Omega angular frequency, C capacitance value, V obviously the applied voltage. And V by R is the current flowing through a resistance. Or I can write in another way, instead of omega CV, I will write it as IR. Instead of V by R, I write it as IA. So let's see what are they. I will define this omega CV or IR as the displacement current, and V by R or V is the conduction current. So I is equal to V by R is something which we already knew that it exists, but now we also have the displacement current coming into picture. So the conduction current is a real term while the displacement current is an imaginary term. The sum of both results into the total current. So obviously the total current is now a complex function. Now let me just plot the imaginary versus the real part, or better I can say that I am going to consider the total current vector I and resolve into two components. One is the imaginary part, another one is the real part. So the real part IA, there is a condition current, remains in x-axis, and the imaginary part IR, there is a displacement current, remains in the y-axis. Now so I have basically resolved the total current vector into its real and imaginary part. Now the angle made by the total current with respect to the displacement current is known as loss angle. LOSS, it's over here, loss angle, delta. And this delta, so if this angle is phi, then since this is a right angle, then I'll get delta is 90 minus phi. So conduction current will be always in the same direction as the voltage. So between voltage and current here, the angle was phi. So delta is the angle between the total current and the displacement current. If I find tan delta, if I take tan delta here, I get opposite side by adjacent. So that is IA divided by IR, or conduction current divided by displacement current. That results into 1 by omega CR. This tan delta, you call it as loss tangent or dissipation factor. I am going to define in a similar way based on the dielectric constant or the relative permittivity. So relative permittivity also is going to be a complex component. So I can represent once again that the relative permittivity epsilon r star is a sum of the real component. Sorry, this is not minus, it should be plus over here. Sum of the real component and the imaginary component. So epsilon r prime as real and epsilon r double prime as the imaginary, j as the vector. Okay, so there is a small mistake here in what I have written in my notes. So this should be epsilon r double prime. The real should be epsilon r double prime and imaginary should be epsilon r prime. So once again, I resolve the relative permittivity vector epsilon r star into 2. The real function on the x-axis, that is epsilon r double prime, and the imaginary term on the y-axis, epsilon r prime. So I can again define delta, the loss angle, and tan delta, that is the loss tangent. So tan delta I am going to get as epsilon r double prime divided by epsilon r prime. So loss tangent, I will call it as the loss tangent. Now if I just multiply this epsilon r prime into tan delta, what I get will be epsilon r double prime. That is the real part. I will term this as a loss factor. How much factor is the dielectric loss happening is given by epsilon r prime into tan delta. So here I also shown a lossy dielectric. So whenever I have a capacitance with a dielectric, and I also included a resistance across it to consider to understand the loss in both conduction current and the displacement current. So now what we are going to do next is the frequency dependency of polarization. It's the whatever is the curve which I am going to plot, it's also known as the dielectric loss spectrum. So as we said earlier, so what I have considered is in the x-axis is the frequency and y-axis dielectric constant. And since electronic polarization occurs very fast, so time taken is very less. So frequency is always inversely proportional. So the 1 over t is what is frequency. If time is less, then frequency will be higher. Whereas in case of orientation polarization, time taken is more, so frequency will be lesser. And at the same time, we already saw that more polarization occurs, more polarization, or we get more dielectric constant in the case of orientation polarization. So orientation polarization occurs at lower frequencies. Ionic polarization extends slightly to mid-range, and electronic polarization occurs till higher frequency. So this is a plot of the frequency dependency of polarization, or frequency dependency of dielectric constant in the different types of polarization. Space charge polarization, we already talked that it is negligible, so we need not consider about it. So that's all about in this particular lecture. So watch out for my next lecture, which will be on the internal fields, and there is one coming up on the ferroelectric materials and also on the applications. And I'm also planning to come with some numericals so that it will be easier for you people also to do along with me. Thank you.